to this lighter PhD seminar after the vacation, and I hope you have had a great vacation. And today we have two great talks from two doctors who got their title just before summer. So first, Wilhelm will present his thesis on exploring structural carbon fiber composites for massless energy and actuation. So Willy, please, the floor is yours.
Thank you, Fang. There we go. Do we actually see this?
Yes, I can see your screen, but not, yeah, now it's in the presenting.
Right. So you can see the presentation, all right?
Yes, we can.
Great, thank you. Thank you for the introduction. So I'm going to talk about my PhD in structural batteries, essentially. So that's basically what we're talking about. We're also talking about a little bit about actuation. So there is a growing demand to decrease energy consumption for transportation. And one way to make such a decrease is by making lighter and thus more fuel efficient vehicles. Using carbon fiber composite, magnesium or other lightweight material is one way to make things lighter. But another way is to make things do more things at the same time, thus reducing the need to make separate parts and connectors. This is called making a system multifunctional. Also, materials can be multifunctional. For instance, in this research, we have shown a way to make a structural material that can also store electrical energy. This is called a structural battery. The idea is simple, but in order to understand what I've been doing in this research, we need to start with some basics on how a lithium-ion battery works. On the left in this image, we have a positive electrode layer. It consists of an aluminum foil coated with lithium-rich powder. On the other side, we have the negative electrode layer consisting of copper foil coated with graphite powder. The two electrodes are submerged in an electrolyte which contain lithium ions. If the two electrodes would physically touch each other, the battery would short circuit. In order to prevent this, a separated layer is also present in the electrolyte. When charging this battery, electrical energy is added to the two electrodes, which makes electron move from the positive electrode to the negative. The lithium ions will then move at the same time as the electrons, but through the electrolyte instead, until the negative electrode is completely filled with lithium ions. This charging is then made in the opposite direction. This time, the reaction starts when the battery terminals are connected to something consuming power. The electrons and lithium ions flow back to the positive electron, and it's this flow of electrons that is used to power devices like light bulbs and electric motors. So that's the battery, but a structural battery also needs a structure. So now we jump over to the field of carbon fiber composites. Carbon fiber filaments are roughly 5 microns in diameter and mostly made from graphite. They are bunched into threads of thousands of filaments, which are then commonly woven into a fabric. The fabric in itself is not specifically useful. It cannot be used to carry load, and it's very brittle. The fabrics are put together in layers, and the magic happens when this fabric is combined with a matrix, a liquid mix of monomers that polymerize and solidify around the fibers by a chemical reaction. This mix is often epoxy or vinyl ester, and is not particularly useful on its own due to its low mechanical properties. The fibers are carrying the load, and the matrix is distributing the load between the fiber. This combined material is now called a composite, with which we can create parts that are extremely lightweight, stiff, and strong. So we have actually seen that lithium-ion batteries and carbon fiber composites are similar in their layered construction. It has also been shown that carbon fibers can do the work as the negative electrode in a lithium-ion battery. The carbon fibers can both store lithium ions as well as being electrically conductive, meaning that the copper foil and the graphite powder can be replaced with carbon fibers. However, this is all still in a liquid electrolyte, meaning that the carbon fibers do not have the ability to carry load. In order for the carbon fibers to be able to carry load, we would need a solid material similar to the matrix to support the fibers and distribute the load, while also maintaining the ion conduction made possible by the liquid electrolyte. The first part of my research has focused on bringing the worlds of batteries and structures together by investigating a matrix material which both distribute mechanical load as well as conduct lithium ions. We call this new matrix material a structural battery electrolyte. First, let's investigate if the structural battery electrolyte can conduct lithium ions. The structural battery electrolyte is made by mixing a liquid electrolyte and a liquid monomer, both of which are specifically chosen to be soluble in each other, forming an homogeneous mixture. As the monomer begins to polymerize and solidify, the solubility changes and the two components separate into two distinct phases, like shaken oil in water. When the monomer solidifies, it creates a solid but porous backbone through which the electrolyte and lithium ions can flow. Here we see SEM images of 3 different versions of the structural battery electrolyte, where we can see a sponge-like structure of the polymer phase. This is showing that the phase separation is at a small scale. In order to check whether lithium ions can flow through this material, we tested the battery functionality. The graphs show that we are able to fill and remove carbon fibers with lithium ions when they are inside the structural battery electrolyte. Specifically, the x-axis shows capacity of the carbon fibers in the structural battery electrolyte, which is not very far from that of pure graphite at 372 milliampere hours per gram. This shows that the structural battery electrolyte can conduct lithium ions. But what about the carrying load? For this, we investigate the stiffness and strength of the structural battery electrolyte combined with carbon fibers. This is done by testing samples in 3-point bending and measuring the stiffness and load at failure. The data shows examples of results in the longitudinal and transverse direction in relation to the carbon fibers. The values are between 90% and 50% as good as samples with pure vinyl ester. This shows that the structural battery electrolyte can sufficiently distribute loads to the carbon fibers to carry load. The structural battery electrolyte is a porous material of solid and liquid phases. This porosity is present all the way to the surface of the carbon fibers. And this is in order to have both ion conduction to the fibers, but also adhering mechanically to them. Since the adhesive contact surface is reduced, the adhesive strength will be reduced. We would like to know how large this reduction is. To characterize the adhesive properties between carbon fibers and the structured battery electrolyte, a drop of monomer and electrolyte is placed on a single carbon fiber and solidified into a droplet. The droplet is held by steel blades and the fibers pulled out. This is measuring the adhesive interfacial shear strength. The results show that the structural battery electrolyte is not far from pure vinyl ester in adhesive properties, even though the adhesive surface area is greatly reduced by the phase separation of the structural battery electrolyte. So we can swap out the copper and graphite powder of the negative electrode and replace it with carbon fibers. And we can alter the electrolyte to create a true composite material with those fibers and the structural battery electrolyte. But this is only 2 of the 3 parts we need for a functioning battery. We still need a positive electrode, which we would create by combining carbon fibers in lithium-rich powder. This would be completing our battery and further strengthening our structure due to the extra fibers. The question is then, will this structured battery save weight versus lithium-ion battery and carbon fiber structure? We have been wanting to make a complete structured battery by implementing coated carbon fibers as positive electrodes, but there has been some challenges making this happen due to corrosion and cell layout. Nevertheless, we've investigated this question with a modeling approach. In this model, some of the components for the structured battery are considered variables. Let's look at the weight saving from some of these variables. In this graph, we see the weight saving of the structured battery as a function of the amount of carbon fibers in the positive electrode. Positive numbers means that the structured battery will save weight, and we can see that we should have a large amount of carbon fibers to improve weight saving. The same trend is visible for the negative electrode. More fibers mean more weight saving. For the separator, on the other hand, it should instead be as thin as possible, whereas any improvements to the conductivity of the structured battery electrolyte are beneficial. These results highlight that the amount of weight that can be saved depends on the internal design of the structured battery. The results help with understanding on how to design the structured battery in order to increase its ability to save mass. The structured battery is now shown in the use case of an electric car. It is designed as the roof of the car, and it will weigh about 9.6 kilograms with the improvements from the previous slide. A steel roof with the same stiffness and a lithium-ion battery with the same total energy storage as the structured battery would then weigh 25 kilograms, meaning that replacing this battery and steel roof, it would save about 60% in weight. If we instead compare the structured battery to the best available, a carbon fiber composite and a lithium-ion battery, they would weigh about 12 kilograms together. This is still showing about 20% weight saving by using the structured battery. But pure weight saving is not the only relevant factor in material design. It is also important to understand what are the environmental footprint of the manufacturing, usage, and recycling of the structured battery. These properties are analyzed in what's called a life cycle assessment. We are calculating CO2 emissions, ozone formation, and resource depletion. Here, an example of the results are shown for CO2 emissions by using a structured battery in the roof of an electric vehicle compared to a steel roof and separate lithium-ion battery with the same energy storage. Negative values show a decrease in emissions by using a structured battery. Driving a vehicle with structured battery in EU saves more CO2 than when driving in Sweden. Interestingly, this is due to an on average cleaner energy mix in Sweden, leading to a smaller gain from the reduced weight of the structured battery. However, the cleaner energy mix means a reduced CO2 when the structured battery is manufactured in Sweden. In general, these results show that the structured battery will reduce the environmental footprint. Understanding these concepts can be challenging, even for professionals in materials and batteries. Interestingly, in industry and academia, the structured battery design and the battery design are usually, the structural design and the battery design are usually completely separate. They also have different metrics to compare designs. For example, in the battery sector, the energy per mass, called specific energy, is central, whereas for structural engineers, Young's modulus divided by mass is a common metric. For structured batteries, these properties will always be lower, since the material is also performing a second function, meaning that with the given comparison, the structured battery will never be chosen. We need to look at the sum of its parts. As an example on how to do this in a new way, we can start by asking how good a lithium-ion battery must be to compete with a structured battery. By taking the mass of the structured battery and subtracting the mass of an equivalent carbon fiber structure, The remainder is what a lithium-ion battery is allowed to weigh in order to have the same weight as the structural battery. This allowed mass is then given an equivalent residual specific energy performance for the performance of the structural battery. Using this method better highlights the potential gain from using the structural battery in a single and common metric. So we've seen a lot of information about structured batteries, but there is another phenomenon in carbon fibers that we can use. As a carbon fiber is filled with lithium ions, the volume of the material increases. This is also reversible, so when removing the lithium, the carbon fiber shrinks again. Actually, this is also present in normal lithium-ion batteries, where it's related to battery degradation. However, for the carbon fibers, this can be utilized to make materials that can change shape. We have taken this phenomenon and created such a material. Here we see a 3-layer composite with 2 layers of carbon fibers and a separator, all of which are in the structural battery electrolyte. The carbon fibers are activated with lithium ions to 50% of their total capacity. Now, running a current from one side to the other means we are moving the lithium ions from the carbon fiber on one side to the other. This means that one layer gets filled with lithium ions and the other gets emptied. What happens then is that the carbon fibers in the layer that gets filled expands, while the carbon fibers in the one that gets emptied contracts. However, the real case does not really look like this. It looks like this. The expansion and contraction of the carbon fiber layers leads to a bending motion of the stiff and structural carbon fiber material. We're going to see a video of this bending movement. The video is fast forward. We can see hours and minutes down here. In the graph, we can follow the voltage difference between the electrodes and the applied current as a function of time. On the right, we see the material, which is clamped on the wall at one end, and the other end is free. This is forming a cantilever beam. A high current is applied, leading to an actuation in about 20 minutes. Next, the current is reversed, then stopped after further 20 minutes to take it back to center. The reverse current is again applied, this time leading to a bending upwards, before one more step of current brings it back to center. This time, the current is lower, leading to a slower but larger deformation. Here we see the material forming a half circle and touching its wall, after which the current is reapplied. And this is bringing the material back to center. Between each step, we've seen an hour-long pause where the 2 electrodes are disconnected. The material is during this pause staying deformed, and this is an important feature of the material, which is called zero power hold. So to conclude, we have seen a structured battery electrolyte. The structured battery electrolyte has been shown to conduct lithium ions required to store electrical energy in carbon fibers. Not only this, but the structured battery electrolyte can at the same time also carry mechanical load and adheres well enough to the carbon fibers to distribute load. This is required for a structured battery to be structural. We have seen that a structured battery made from this material would have the potential to save significant weight compared to equivalent carbon fiber structures and lithium-ion batteries. Not only weight saving, but this structured battery can reduce the environmental footprint in electric vehicles. The research on structured batteries and the structured battery electrolyte has also led to the creation of a new type of stiff composite material that can change shape. I'd like to thank the Funders of this research, the Swedish Research Council, Swedish Energy Agency, LITER, the Age 2020 Clean Sky 2 project, and the Air Force Office of Scientific Research. I've had many collaborations during this research, namely with colleagues and friends at Chalmers University, Luleå Technical University, British College London, Airbus, RISE, and MBA Institute. I'd like to make a special thank you to Oxion for supplying carbon fibers used in this research, and also my research group Combat for great teamwork. I'd like to thank all colleagues and friends at my departments, engineering mechanics, chemical engineering, and fiber and polymer technology. Thank you for listening.
Yeah, thank you so much. Fantastic, very clear presentation, and fascinating to see the composite material can bend to a curve.
Thank you.
Any questions from the audience? Everything is super clear?
Mm-hmm.
Yeah, there are many PhD students in the network. So actually, I won't ask you something technical.
Mm-hmm.
It's more, you published an article in PNAS. That is a very high-ranking journal. Do you have any experience to share with your peers in the network regarding how to publish in high-ranking journals?
Sorry, can you take that question again?
Yeah. So you have a very nice publication in the prestigious journal PNAS.
Yeah.
So could you please share your experience with
yeah,
the peers?
The article in question is related to the actuation that you saw last within the presentation. It was a bit of a ride.